Imagine trying to simulate a robot picking up a crumpled piece of paper. If you treat that paper like a rigid block, it will never work. It will either pass through the table or float like a ghost. This is the fundamental failure of rigid body physics when applied to soft or deformable objects. In the world of robotic manipulation training, we often assume objects are solid and unchanging. But reality is messy. Materials stretch, compress, and slide in ways that simple collision boxes cannot capture. To bridge this gap, we need to move beyond simple rigid bodies. We are looking at universal scene description physics, commonly known as USD physics. This framework allows us to define physical properties not just for solid blocks, but for complex systems where geometry changes during interaction. The challenge lies in the setup. You cannot simply export a high-fidelity 3D model and expect the physics engine to understand how it behaves. The visual mesh and the physical mesh are two different things. Here is the thing about collision meshes. High-fidelity geometry is often too detailed for physics solvers. Imagine trying to calculate the friction of a surface that has microscopic bumps and valleys rendered in millions of polygons. The simulation will either crash or behave unpredictably. The solution is to decouple the visual representation from the physical one. You create a simplified collision mesh that approximates the shape but removes the geometric noise. For rigid objects, this might mean using convex hulls. For soft bodies, it involves defining constraint points and spring forces. This simplification ensures the solver can resolve contacts stably without getting bogged down by visual detail. You are essentially trading visual perfection for computational stability. Once the geometry is handled, you must address mass. This is where visual data fails completely. You can look at a 3D model of a steel ball and a plastic ball, and they might look identical in shape and size, but their mass is vastly different. If you assign them the same mass in the simulation, the robot will lift the plastic ball as if it were steel. This leads to simulation drift, where the virtual robot fails to replicate real-world behavior. Current research suggests that automated pipelines are necessary for this. Systems like Scalable Real-2Sim utilize robotic pick-and-place sets to physically interact with objects. By measuring the force required to lift an object, the system infers the mass and inertia. This physical grounding ensures that the digital twin knows exactly how heavy an object is, rather than guessing based on density assumptions. Now consider friction and restitution. These are the parameters that determine how an object slides or bounces. Without accurate estimation, even a perfect mass assignment will result in a simulation that feels wrong. A rubber ball should bounce differently than a glass marble. In traditional workflows, engineers would manually tune these numbers until the simulation looked right. This is inefficient and prone to error. Newer approaches are changing this. Some methods use machine learning models to infer these properties from visual data alone, while others rely on sensor fusion during the asset generation phase. For example, PhysSplat proposes using large language models to guide Gaussian splatting techniques to infer properties without physical interaction. However, for manipulation training, the most reliable method remains active estimation. By running the asset through a series of controlled interactions, you can derive the friction coefficients and restitution values that match the real material. This becomes even more critical when dealing with soft bodies. Rigid body assumptions fail because the object deforms under load. A sponge will compress when squeezed. A cloth will drape over a surface. USD physics allows you to define these behaviors through material properties rather than just shape. You define stiffness, damping, and volume preservation. The key is that these properties must be calibrated against physical reality. If you get the stiffness wrong, a virtual cloth will hang like a steel curtain. If you get the damping wrong, it will oscillate forever. This is why parameter estimation is not a one-time step. It is an iterative process of matching simulation output to real-world sensor data. So, what does the actual workflow look like? You start by identifying the asset category. Is it a rigid tool or a deformable material? You generate the collision mesh, ensuring it is convex or compound enough for the solver to handle. Then you estimate the mass and inertia. If you have access to a robotic setup, you perform physical measurements. If you do not, you rely on data-driven inference from similar assets. Finally, you calibrate the friction and restitution. This might involve running a sliding test in the simulation and adjusting the coefficients until the motion profile matches recorded data. This entire pipeline is designed to ensure sim-to-real transfer. The goal is not just a pretty simulation, but a functional one where the policies learned in the virtual world work immediately in the physical world. Thanks for watching all the way to the end. I am a one-person team working hard to make each video better than the last. Subscribe if you found value. It is the best way to show support. Drop a comment with your biggest takeaway. See you in the next video.